Hello again everybody, welcome back to Glaciers and Glacial Geomorphology and to the second of our two lectures in this session on glacier hydrology and meltwater. In the previous video we talked about water in glaciers and the way it's controlled by the thermal regime, and we talked about some of the ways in which it influences glacier behaviour, including glacier dynamics, glacial geomorphology and so on. In this session I want to talk specifically about water in sediment transfer and glacial geomorphic processes, because we're moving on towards the section of the module which is talking specifically about geomorphology. And I'm talking now about meltwater both in the glacial and in the proglacial environment. So this video is just finishing off what we started talking about in the previous one as we move forwards now towards the geomorphology section of the module. So the first basic point that I want to make is that meltwater from glaciers can tell us about what's going on inside the glacier and underneath the glacier. The meltwater is another of the pieces of evidence that we can read to figure out what's going on within the glacier system. And there are a couple of images here that illustrate meltwater emerging from the fronts of glaciers. In fact, both of these scenes are on the west side of the Greenland ice sheet, just above the Arctic Circle, around the Russell Glacier area. But in both pictures you can see water coming out from the glacier, and you can pick out a number of important characteristics at this stage that we're going to come back to later on. The first is that very often in a glacial environment, water is associated with a plentiful debris supply. The second key characteristic of meltwater in glacial environments is that typically it's extremely variable in its discharge, and that includes both discharge of water, because different amounts of water are being produced by the glacier at different times of year. Lots of meltwater typically in the summer, much less or no meltwater typically in the winter. So the discharge of meltwater streams varies a lot throughout the year, and associated with that discharge variability there's also a variability in the sediment discharge. So a number of different factors that we're going to see cropping up over and over again as we talk through some issues surrounding meltwater in glacial environments. And that point about discharge variability is picked up in this diagram from Patterson's Physics of Glaciers book that shows meltwater discharge from a glaciated basin near Zermatt in Switzerland over the course of a developing season. So what this graph is showing is discharge, river discharge, meltwater stream discharge on 4 separate occasions over 4-day periods on each occasion, beginning early in the season at the bottom of the graph and moving through into full high season at the top of the graph. And at the bottom of the graph there you can see that the daily variability is relatively low and the total discharge is relatively low. So early in the season there isn't much water about yet, and there isn't that much difference between daytime and nighttime discharge. But as we move forward into the year, the total amount of water being produced increases. There's more meltwater later in the year than there is earlier in the year, but also the diurnal variability increases as we move forward into the year, with higher peaks each day compared with the overnight troughs in meltwater production and delivery. You'll also notice that as we move forward into the year, the timing of the peak discharge each day gets a little bit earlier, because not only the amounts of water but also the timings of the throughput of water during the course of the day vary through the season. So that's the first point I really wanted to make about meltwater, is that compared with many other streams it's highly variable, both on a long-term basis as glaciers come and go, and on a seasonal basis as glaciers produce more meltwater at some points in the year than others, and also on a daily basis as more meltwater is produced at some times of day and less at other times of day. And there's also this throughput time, so you'll get a different peak, different timing of peak, depending on where you are in the glacier system and how big the catchment area is for the stream that you're measuring the discharge in. So lots of different things contributing to this variability in measurements. Now, because there's lots of debris, lots of sediment available in typical glacier systems, we're interested not only in water discharge and its variability, but also in sediment discharge and its variability. And these two pictures, both taken from around Sólheimajökull in southern Iceland, they just illustrate that there can be a lot of debris within glacial meltwater. The little stream coming out of the front of Sólheimajökull here almost looks like a chocolate stream. It's so full of debris, and when you stand on the hilltop and stand on the hilltop and look down at the outwash coming away from the front of Solheim. I'll call the land rover there for scale, just to give you an indication of what it is that you're looking at here. The Sander plain is full of debris, and we have this braided river channel pattern which reflects the variability in the water discharge and the high sediment availability in that environment. Also, I've just marked in here some ice block marks indicating again the variability of discharge. This was underwater at some point when there was high water discharge, and there were ice blocks, little icebergs from the front of the glacier being carried downstream, and these got deposited possibly in a waning flow as the discharge diminished again, and were left behind, stranded on the Sander surface. So there's lots of variability through time, not only in the water but also in the sediment. And to some extent, the sediment and meltwater discharge varies together. As you have more water coming through, you think, well, you can carry more sediment then, and that's true to some extent, but it isn't entirely true. And as you'll read in the background reading in the textbook for this session, you'll read up on how there is more sediment available within the glacier at some times of year and less at other times of year. So early in the season, after basal debris has built up because of erosion but no meltwater flushing of the bed during the winter, early in the season the bed can be flushed and lots of debris is available for carrying away. So if you have a high discharge early in the season, it's likely to be carrying a lot of debris with it. Whereas later in the season, after the basal environment has essentially been cleaned out and hasn't generated new debris by erosion to replace that cleaned out debris, if you have a high discharge later in the season, it won't necessarily have as much debris to pick up and evacuate. So you might not get the same peak in sediment discharge matching the fluvial discharge that you did earlier in the season. So just be aware, sometimes there's a synchronicity between the water discharge and the sediment discharge if there's plenty of sediment available, but if there isn't sediment available at any location at any time, then you won't necessarily get the peak sediment discharge matching with the peak water discharge. But as I mentioned earlier, one of the key characteristics that we're going to be looking at glacial meltwater environments under the heading of geomorphology later on is thinking about the way that meltwater river channels respond to that driving characteristic, or those two driving characteristics: discharge variability. So sometimes there's loads of water, so if there's sediment it can carry it. At other times there's much less water, so if there is sediment being carried along, less of it will be carried at some times. There'll be deposition in the channel. And because we do typically have high sediment availability in these kinds of glacial environments, there's lots of sediment around, highly variable discharge, and that gives us this typical braided river channel. Now, as well as thinking of debris and sediment discharge within meltwater, we can also think about chemical discharge, or the chemical composition of meltwater. And glacial meltwaters are often rich in dissolved impurities, or they're rich in solutes. There are a variety of biogeochemical processes that go on within glacier systems, but in the context of what we're going to be carrying on to talk about with the geomorphology, one of the major controls on chemical composition of meltwaters is the contact that the water has had with the glacier bed or with minerals within the glacier, for example, within the basal ice layer. In other words, the pathway that the water has followed and how long the water has taken to travel through that pathway. In other words, how long it's been in contact with the bed or with debris within the glacier to actually interact with it to obtain these solutes from the debris. So typically there are variations between winter and summer outflow, and there are variations in the chemistry of water which has travelled quickly through the system and hasn't been in contact so much with minerals or with the bed, and slow flowing pathways, or water which has been stored up at the bed of the glacier or in contact with debris in the basal ice, for example. And so that enables us, from the chemistry of the meltwaters, to say something about the pathway that the water has travelled through the glacier, and a lot of work has been done using that chemical evidence to reconstruct meltwater pathways through glacier systems on the basis of geographical and temporal variations in solute composition within the meltwater. A fourth heading, or a fourth topic, that I should just draw your attention to as I send you off into the literature to do your reading, is the topic of ice-dammed lakes or glacial lakes and the floods that can result from the release of those lakes, or from the release of water stored within glacier systems. So you may have come across the term jökulhlaup, which is an Icelandic term, and it means, well, literally it means a glacier leap. A leap being a leap in the water level of a stream, so in other words a flood, and jökull to do with a glacier. So a flood in a stream to do with things happening in a glacier is what jökulhlaup is talking about. Another term that's often used now is glacier lake outburst flood, or GLOF, which I suppose in a sense is more specific because that does refer to glacier lakes, whereas a jökulhlaup can result from a variety of different factors, including a subglacial volcanic eruption. But there are all sorts of different flood events that can occur as a result of the release of stored water from within a glacier system, which might be an interior subglacial water storage, a supraglacial lake suddenly draining through the end glacial system and emerging at the front of the glacier, or an ice dammed lake, a lake water held up behind a glacier, which is released by failure, for example, of the ice dam which is holding it up. You can also think about moraine dammed lakes, or those are perhaps a slightly different category of event, but they're another example of how water in the glacier system is potentially, well, a hazard from a human perspective, but how one of the potentials for its activity in the landscape is to do with the storage and abrupt release of meltwater in the form of floods from lakes or other storage points within the glaciological system. I'm just going to give you some examples at different scales, and this is a really tiny little example. This is at the edge of Salheimjökull, so we have the valley side on the right hand side of the image here, going down into the valley, and the glacier here is filling that valley. So here's the edge of the glacier, and Salheimjökull here, lots of supraglacial debris, lots of volcanic tephra on the glacier surface, but you can see a trim line here, which is the former lake shoreline, separating out dirtier ice surface above and cleaner ice surface below, where the lake used to be filling in, and you can just about pick out shorelines around here as well, and you can envisage how the lake was ponded up against the side of the glacier. There's a figure there for scale. And then as a result of pressure or melting from the water, or more likely in this case movement of the ice downstream, the ice here is moving from right to left, essentially a passageway opened up at the bottom of this lake, and the water was able to escape into the subglacial system, and so the lake disappeared. So this is an example of an ephemeral or temporary ice marginal lake, and by the time we got here to take the photograph it had disappeared already, but it left behind its mark in the landscape, a very temporary mark on the side of the glacier here, but a potentially slightly more long-lived mark on the hillside here. And at bigger scales, shorelines of lakes of this type that have been dammed up between a terrestrial surface and an ice body, those marks can persist for thousands or tens of thousands of years into the future. For example, I'm going to talk about the Missoula flood in a second, and one of the many interesting landforms associated with glacial Lake Missoula in North America are a series of shorelines left behind on the hillsides of Missoula. Now this is a slightly larger example. This is from again this is the Russell Glacier in West Greenland, and this is an example of exactly the same kind of thing, an ice dammed lake, but here we're talking about a lake not just a few meters across like the Salheimjökull example that you saw, but several hundreds of meters across. To give you an idea of scale, from here right at the top of this ice marginal lake basin all the way down to the bottom edge of it here is probably well over a kilometer or thereabouts. So we're looking at about a kilometer diameter there for the long axis of the lake. And what you're seeing here is an ice dammed lake ponded up in this area. You can actually just about pick out on this image that the lake basin is half full when this image was taken. You can see a pale outline of an outer shoreline and the slightly darker patch, which is the water in situ at the point when this air photo was taken. Now, when this lake is dammed up at the edge of the glacier here and it fills up, typically it overspills into a drainage system that runs through the countryside around the front of the glacier and off down and out to the sea off to the left of the photograph. But occasionally, if this ice damming up the the lake isn't secure enough to keep it dammed up. So for example, if the glacier retreats a bit and this ice gets thinner, then instead of spilling over the back end of the lake here and into the regular drainage system, instead water is allowed to escape into the glacier because there's an adverse slope here pushing the water back towards the glacier. And so if that dam gives way, the seal which is holding back this water gives way and the water escapes through the glacier and emerges as a major flood into the exiting the glacier here into the drainage system. There's a big delta just in there, and then big floods travel on downstream, and there's a record of those in the geomorphology of the stream down glacier from that location. And this is an image of what that lake looks like when it's full, so that the lake is kind of overspilling at the edge of the basin over there because it's held up, dammed up by this glacier which is holding the lake in place against it. And a lot of you might have seen this photograph before, that this photograph at the top of the page there, a lot of you might have seen that before. One of my favourite photographs from West Greenland. These are icebergs which are floating around in that ice-dammed lake. And this is a view from a couple of miles away, looking across towards the position of that lake on the far side of this hill. And this is the overspill from that lake. So the waterfall coming down here indicates that the lake, just out of sight behind that hilltop there, is currently full and overspilling. And it's being held in place, it's being dammed in place by this section of the glacier here. This delta here isn't created by the regular melt water that you're seeing right now coming off this section of the glacier and making its way through that delta into the lake. The delta is created when the ice dam up here gives way and water from that lake gushes through here, and as a major flood bursts out from the edge of the glacier here, and it's those events that creates these deltas and has additional effects downstream. And this is one of those downstream locations. This is several miles downstream from the lake, and you can see on the far side of the river here a few tents for scale. And this is a photograph of the stream, obviously not in one of those flood periods. And just to give you an idea of scale, the dot that you can see on the beach on the far side of the river there, that's a chap who's about 2 meters tall, well over 6 foot tall. So you can see there's quite a drop from that shoreline up there where the vegetation begins, down past that chap, and then down again, and then down again to the water level. And this is the water level that we typically would encounter around about September when there isn't a flood going on. But the next photograph was taken in more or less the same spot, maybe just standing back a few yards to include more from this side of the valley. But if we look at the next scene, you can see that during one of these floods, the entire channel is filled. So where the tall chap was standing in the previous photograph was just over here somewhere, and those tents were just over here somewhere. But that entire channel, if I just flick backwards, all the way up to the level of the vegetation on the bank. So there's 6 foot, 12 foot, maybe 18 foot, 6 meters, 7 meters. All of that depth is filled by the water in the channel when these floods occur. And at this stage the channel is at about bank full capacity. The water is just up to the edge of the vegetation, indicating that the channel is adapted or is balanced to this particular discharge. So the discharge that we more typically see, the channel isn't in equilibrium with that. The channel is in equilibrium with these major floods, even though they come down much less frequently. So if you think back to what you might have studied previously in first year with us, thinking about things such as magnitude and frequency, this is a nice example of how a high magnitude, low frequency event is actually dominating the morphology of the channel in this location. And this is another section of that same channel further upstream. And again, this photo was taken during a typical summer peak discharge when there aren't floods. So you can see there are still huge areas of bed forms exposed, not underwater, even though we're at the height of the melt season here. And again, it's because all these bed forms, all this geomorphology, this fluvial geomorphology, isn't related to the normal meltwater system. It's related to the occasional floods that run through this part of the system. So this is another aspect of that variability. We have diurnal variability, we have seasonal variability, we also have long-term variability in terms of glaciers coming and going. But in between those short and long-term variabilities, we also have these occasional major events which can have a massive impact on the geomorphology. It isn't necessarily the routine events that do the geomorphological work. It's sometimes the extraordinary events. And we can read that by looking at evidence such as these ice block marks and mega bed forms that clearly relate to discharges, to flows much bigger than the normal summer meltwater discharge. But moving up the scale, I'm not going to talk about these in detail, but I just want to alert you to a number of big examples of glacial lakes and ice-dammed lakes and floods that are associated with them. And these, the examples I've given you previously from what I've seen in Iceland and Greenland, these next two examples just make those seem completely insignificant compared with the scale of these. And the first one that I'm just bringing to your attention here is Glacial Lake Agassiz, which was an ice-dammed lake, but as you can see from the map here, it's an ice-dammed lake covering a huge area of what's now on the boundary between the USA and Canada, dammed up against the remnants of the Laurentide ice sheet as it's retreating. And periodic catastrophic drainage from Lake Agassiz is one of the contributing factors to really interesting patterns of sediment, iceberg rafting, sediment discharge, and connectivities between the terrestrial meltwater system and the ocean system. So Glacial Lake Agassiz and its occasional catastrophic outbursts through the Laurentide ice sheet is a really interesting topic, both for glaciology and for geomorphology and for environmental reconstruction. And one more case study that, again, I just want to bring to your attention. You can look it up and read more about it. But another big example of glacial outburst floods from the release of ice-dammed lakes are the Missoula floods. And the photograph at the top here shows an area, part of an area called the Channeled Scablands in Washington State of the USA. And this highly eroded landscape was created by outbursts of water released from Lake Missoula, which is another lake which was penned up or dammed up against the edge of the retreating Laurentide ice sheet. There are other examples from around the world. Look, for example, at the Altai floods from Central Asia. That's another example of ice-dammed lakes having a massive catastrophic effect on landscape. But a North American example that many of you might have heard of previously and will crop up in other parts of some of the courses that you're doing are the Missoula floods. And here's a map that kind of gives you an idea of the scale of impact of floods such as this, whereas the Solheimjökull and Greenland examples I were giving you were operating on the scale of a few kilometers or tens of kilometers. Here we're talking on floods that are operating on essentially a continental scale. So here's the town of Missoula. I mentioned before there's spectacular shorelines on the hillsides around Missoula marking levels of the lake when it was dammed up in this area behind the retreating Laurentide ice sheet. But then this map shows the flood route through the Channeled Scablands. Moses Lake area is somewhere around there was where I was taking those photographs of the Channeled Scablands west of Spokane. And the water made its way all the way through this territory and across to exit into the ocean out here on the west coast. So as you can see from this map showing the chunk of North America, this is a very large scale system with huge volumes of water having a massive effect on the landscape. So these are not trivial phenomena, and they have a major impact on landscape that, as in the case of the Missoula floods, the landscape impact has survived since the end of the last ice age as a major component of the North American landscape in this region. So I haven't really dwelt on anything to give you a huge amount of detail on any of those topics, but I hope I've given you some signposts just to encourage you to go off and look at the literature in a little bit more detail and find out a little bit more about each of those topics. So in the last video we talked about how water is important within glacier systems. What I hope I've done in this video is just draw your attention to the fact that water is also important when we start looking at the connections between glaciers and geomorphology, and we start thinking about the geomorphic impacts of glaciers, not just the indirect impact of water on geomorphology through its control on ice dynamics, but also the direct impact of meltwater on geomorphology within that broader glacier and landscape system that includes the glaciers, the sediment, the meltwater, and the environment within which they're all working together to give us these complex landscapes. So be aware that meltwater is important in sediment transfer. Also remember what I said about there being a chemical component or a solute component to what's going on in meltwater, and that can tell us about processes operating within the glacier as well. Bear in mind that meltwater, as well as ice, is really important in geomorphology. Think specifically about, for example, fluvio-glacial landforms, and think particularly about special events, if you like, such as glacial outburst floods. And what we're going to do next is move the module forwards essentially into the final section of this module, where we're going to start talking much more specifically about geomorphic processes and the impact of those on geomorphology. And what you need to be doing over these next few sessions is taking on board this new geomorphological content, but also trying to relate it back to the glaciological content, because one of the things we're trying to do is recognize how glaciological characteristics of glaciers such as ice dynamics, are important in determining the landforms and landscapes that glaciers leave behind. And because of that, we can use the landforms and landscapes that are left behind to figure out what the glacier must have been doing and what the glacier must have been like that created those landforms. So we can reconstruct glaciers on the basis of the landforms that they've left behind. And that's what we'll be moving on to in the next section of the module.